this will be from 6 to 8 place nearby water dealers selected by our team, and we went out last night and tried the dealer's excellent food in the Kenya. So tomorrow, super exciting morning, we are traveling to the site of the Old River Bridge, and I'm sure that we are all look at the location, was a pretty long drive, approximately 1 hour and a half. The idea is just to go there with our own vehicles. So I don't want to spend much time on this. I'm sure that this afternoon we'll have an opportunity to go over it again and everything is relevant. And then finally, in the afternoon, many of you probably don't have much interest in this, but we will have a assessment program. We come back to headquarters of District 7, and the part that is the late part of the afternoon, the one that you see during Iran, indicating that open PCC is the part that you can attend, is the part of the debriefing. If you wish to be around, great. If not, for the SEACON members, I will give you myself an update at the next monthly meeting that is coming. So with this, I concluded the first part of my outline. I wanted to give you a sense of what's happening in the next 2 days so you can plan accordingly. Now I want to go into the SEACON project, tell you a little bit about the scope of participants, a little bit about the organization so you understand better the flow, go off the presentations, the rest of the morning. And then the last slide is more the group that everything else just to lighten up the So the scope and participants, as you can see from the slide, we have copied this scope directly from the original program. So we look at the safe utilization of seawater and salt component aggregates for a sustainable concrete production when combined with non-corrosive reinforcement. There's a mouthful of terms, but the fundamental issue, if we are to ask you to put this on a stage, on a postcard, I would say we are looking at concrete without chloride limits and making concrete without chloride limits a material that can be used for structure. So it's all about sustainability, and sustainability can be attained by putting together the right two stages. We're delighted to have 9 organizations among the partners and collaborators. And you can see 4 in the US and 5 in Europe. In particular, even though
is not doing anything,
operations
X is doing everything.
not only subcontinent but really worldwide. And the interesting part in my mind is that we have a combination of academic institutions, UN and polyamine, but also material suppliers and producers and users, and in particular the Department of UT on the user side and academic development on the Italian side. Among the participants that provide the materials, we have ABB with the GFRP bars and Bruno for the stainless steel. Today the focus is very much on the GFRP side, because this is the material of choice of our demonstration project, the Old River Bridge. But when we go to the Italian side, they've done a lot of work led by obviously Polly to the field of the stainless steel. So the idea is the non-corrosive piece, not simply. This is a very crowded slide.
Because when they enter
From this proposal, but it gives you a sense of what are the fundamental work packages. In the European methodology of funding projects, the idea of the work package is central to the way proposals and projects are carried out, and we follow the same format. So we are the WP1 led by Boots and Unison. The materials, which is the line above, and then 2 other work packages, 2 and 3, that deal with the reinforcement types, and then WP4 right underneath it, that is the demonstration project. one in Italy already completed and under monitoring, and one in the US that is really central to this two-day event. The project in Italy will be presented by Dr. Redaelli later today and deals with the construction of culverts along motorway A1. And then to tie everything together, we have WP5 that deals really with the cost and the life of the structures, and Professor Dotelli is here with us and he will give us a presentation. The remaining WPs 6 and 7 deal with management and dissemination deployment, so this is in a sense what we're doing today. This gives you an idea of the timeline. The only thing I want to mention to you, this is a project that started in October 2015. It will end in March of 2018. So we are today in the month of May at the month number 20 of the total that we have at our disposal. So we are in the second month of the last semester. So things are converging, and hopefully we are deploying what we have promised. The last slide is really a collection. You know that I'm very active in the American Concrete Institute. So one of my dear friends provided me with these pictures. So let me explain the title. Is this in unintended, unintentional implementation? The point I want to make is we don't have to go up north to see the infusion of chlorides through de-icing salts in our bridge decks. If you go in this location that is coastal, there is this construction that is going on, a major structure with the tide that moves 12 feet. So when the tide is up and you look at the two pictures on the right-hand side, the foundation is totally covered. And the sticks that you see coming out, these are steel reinforcing bars, black steel. And then when the tide goes down, the picture that is not very clear, taken from a boat from the distance, is everything becomes dry. So the contamination with the chlorides already happens every day in every structure. What is going to be the life of this? I don't know. If you are in the repair business, you love it. But I think the entire point is what we are doing is really relevant, and I hope that not only with this experience in the next 2 days, but with the follow-up of the work that we have generated, there will be interesting follow-ups. With this, I'm going to close, and we will start with the first presentation, and maybe Morteza, you want to help with the transition? As I move away, yes, Catherine will come up. You need this, of course. Clip it. So the next
I'll just hold it.
FHWA actually has been extremely active with colleagues and crew at FHWA in making this a reality from the U.S. side with the Infravation. So we're extremely thankful to her and FHWA for having made this really possible for all of us. Stephanie?
Where's the arrow? So, okay. Well, on behalf of Federal Highway Administration, I'd like to welcome those of you in the room and those of you online to this forum. I thought I'd just spend a couple of minutes giving a little bit of background as to what exactly Infravation is and how we got here. So Infravation, basically the word itself is a mashup of infrastructure and innovation. And it's a transatlantic research program with the goal to look at advancing innovative near-market materials or processes that are going to make highway infrastructure last longer, perform more efficiently, or cost less, and hopefully cost less. So why would we collaborate with the EU? Well, really, highway construction, operations, management, and maintenance is increasingly international. Many of the issues faced on both sides of the Atlantic are common, and there's a lot to be learned from each other. By pooling our resources, we could supplement our own national research budget and then the research of the EU road authorities. So we're leveraging limited resources, and it has the potential then to increase the scale of the projects that we can complete and increase the potential for success. It also provides access to cutting-edge research from both sides of the Atlantic, so we're promoting knowledge sharing and capacity building from each side. So Infravation itself was funded through FHWA in the US, and then the countries you see listed here are the European road authorities and the European Commission in general. So we pooled our resources to create a $10.6 million research program. And what's so special about it? This really is a common pot. There was no guarantee necessarily for those who put their money in that their universities, their industry was going to get a return on that. The funds were pooled, but by participating, the U.S. Was able to allow the U.S. universities industry propose on projects and have access to the results. And then also, the information includes an element of technology transfer and a emphasis on implementation. So we'd like to take the research from the lab to have field demonstrations such as this one. Some of the Federal Highway objectives in terms of participating, it's to provide the opportunity to work directly with each other between the U.S. and the European highway researchers, to assist in harmonizing adoption of new technology and processes, and to provide state DOTs and European national road authorities with common access to innovations. So how did we get here? In 2014, based on that $10.6 million pot of money, we issued an RFP, and we received 103 proposals in response. 2/3 of those proposals included U.S. members. Of those 103, nine of them were awarded, and they were initiated in 2015. Of those 9, 7 included U.S. membership. And then SEACON is one of those 9 projects that was awarded. And you can see it's a collaboration between entities here in the U.S. led by the University of Miami, and then entities in Italy, both academic and industry. So moving forward, as I mentioned, there's an element of focusing on implementation. So we're having field demonstrations, namely this one here for this particular project. And of course, your feedback is welcome. Part of the reason for having this workshop is to hear stakeholder input in terms of where are we, what has been accomplished, what is still needed. And then, as Tony mentioned, there's also going to be a formal technology readiness level assessment following the workshop. And so combining the feedback we get at this workshop, we'll take an assessment in terms of, is there additional laboratory or field testing that's needed? Can we move towards the development of standards or specifications? And then, of course, continuing outreach and training. So with that, I thank you, and we'll welcome your input.
I don't know if there is any question for Kathy. She brought us back into the good part of the agenda, meaning in terms of the time. I don't know if there is any question for her.
Kathy, the 9 projects, they already been identified? Or?
Yes, they're ongoing. Many of them are in final stages now and wrapping up. So in the next year or two, we'll see the outcomes from those projects.
And the technologies are different technologies or all related to the fiber?
No, they're across the infrastructure spectrum.
So the money is already committed there.
Yeah.
Actually, just a comment. We are hoping in a phase 2 of the information. That doesn't guarantee anything to the existing program, but I think it's a very exciting idea. And if you go to the information website, you will see a host of activities.
Yes, infravation.net.
online, and if you want to subscribe, let us know, and we will put you in touch with those. Any other questions for Catherine or comments? Hearing none, thank you, Catherine. She has been very much dedicated to the work that she was, and she will tell us what has happened there in terms of the concrete side. And even though you might have seen a timeline that also doesn't quite true, that the reality is that the monitoring keeps on going because obviously these tests cannot be done.
Okay, good morning all. My name is Federica Bertola from Boots Unicem, and I will present you today the WP1 activities and results, particularly related to the chloride effect on both cement and concrete. So the following are the outlines of my presentation. So the main duties that Boots Unicem has in the project, the European, a brief overview on the European standard related to cement and chloride limits, then the cement that we produced for the SEACON project, the effect that chloride has on the cement hydration, on the physical properties, and on the microstructure, a very short introduction to the ongoing durability studies, and finally the conclusions. The main duties that Boots Unicem have on this project are, first of all, the production of a dedicated cement for the project, and obviously his characterization, the understanding of the effect that chloride from different sources can have on both cement and concrete, the project of different mixed designs for the demonstrator construction, durability studies, and taking part in the Italian demonstrator. First of all, a brief overview in the European standard to understand the difference between the European regulation and the US one. So here you can see the table with the 27 different cements produced and regulated in Europe. They are all including different and variable amounts of clinker, gypsum, and other supplementary cementitious materials that can have or not hydraulic or pozzolanic activities, such as blast furnace slag, silica fume, and so on. So in Europe, there's this trend to add materials during the cement production. And here, the red highlighted items is the SAM 2ALL, so the Portland limestone cement that is considered for all for the entire study. Another important thing that is in the regulation, in the European regulation, is the chloride limit. We have a chloride limit equal to 0.1%, and it's different from the US because you don't have a limit. So this is particularly important for cement producers because we have to control carefully the production of cement to not exceed this limit. So in particular, when we use waste material as an addition in cement, we have to control carefully this limit. So here, the two cements that we consider in the study, a reference cement, so a Portland cement SAM2ALL 42.5, that is commonly produced and sold in Italy. Then SEACON cement. We produced a dedicated cement, as I already told you, for this project, using, in this case, cement kiln dust in partial substitution to natural limestone. In fact, this is a waste material coming from the cement production, and its reuse is limited for his chloride content. In fact, you can see from the table that SEACON cement has a chloride content of 0.23%. The limit is 0.1, so it exceeds the limit, and is very higher compared to the chloride content of the reference cement that is 0.02%. So we perform the characterization of the two cements to understand the effect of this very high chloride content, and we can see that the main effect is on the setting times. So we can say that the chloride content, the high chloride content, can have an acceleration effect in this case. But we decided to continue this investigation, so we produced pastes, so cement plus water, and we consider the two cements with both fresh water and seawater to understand the effect when the presence of chloride is in water, in cement, and both in water and cement. In all the cases in which chloride is present in the mix, we found the formation of brittle salt. This analysis was performed through XRD analysis, and our only concerns about chloride presence and so formation of brittle salt is that an ionic exchange between chloride and sulfate, if available, can happen, and so we are worried about the formation of aggregate that can have an expansive nature and so can create swelling and cracking. So we perform also mortars. Our three mixers were mixed reference with reference cement and fresh water, mixed SEACON with SEACON cement and fresh water, and the third is mixed seawater with reference cement and seawater. In all the cases, we produce mortars according to the European standard UNI EN 196 part 1. So we use 450 grams of cement, 1,350 grams of normalized sand, and 225 grams of water. We use also the mixing procedure of the standard. Then we cure the samples after 24 hours and the molding in three different conditions. So water curing at 20 degrees, dry curing 50% of relative humidities and 20 degrees, and in seawater. And then we perform compressive strength test, and then we determine the weight of the samples to understand if there's a loss or a gain in weight due to the curing conditions. As we can see from the graph, the chloride effect on the compressive strength is not so important, except for mixed SEACON. In fact, in this case, so when chloride are present in the cement, we have a slight decrease in the compressive strength, particularly in the case of seawater curing. And this could be due to the higher absorption of water that you can see from the fourth graph. Then another important thing is that considering the loss of weight, so in dry conditions, mixed seawater has the lower loss of weight. Maybe this is due to the fact that the pores are full of salts in this case, and so the loss of water is lower compared to the other two cases. Then, so we project the different mixed designs, so three in this case: mixed reference, mixed SEACON, and mixed water. The first one as reference, so with reference cement and fresh water. The second one with SEACON cement and in addition of super plasticizer, and mixed seawater that needs also a retarding agent due to the acceleration effect of chloride. We designed them considering a fixed compressive strength of 45 megapascal at 28 days and also desired consistency. You can see in the graph that in all the cases the compressive strength at 28 days exceeds our limit, our target, and that chloride has an effect at 90 days with a slight decrease in compressive strength. In the second table are reported the fresh properties of the three concretes. And you can notice also that chloride has an effect also in the maintenance of workability. In fact, mixed seawater lost more than the other two concretes. Another important property to check is the drying shrinkage. So we performed it in both concrete and mortars to have a comparison. We produced samples, cured them for 24 hours in wet condition, 95% of relative humidity, and then we stored them in dry conditions to see what happened. The results are completely in agreement, so we can say that when a higher chloride content, when we have a higher chloride content, the shrinkage is higher. So the chloride content worsened this behavior, and we thought that it was due to the higher surface tension of the pore solution when oversaturated with salts. We decided also to have some information about the microstructure to better understand this behavior, and so we consider two different techniques, the SEM and the MIP, to understand the microstructure and the distribution of the pores inside the material. So we produced the same mortars that I told you before, so mixed reference, mixed seawater, and mixed SEACON, and we stored them first in water for all the time that we perform the investigation. From the images, you can see that mixed reference has a well structure compared to the other two. In fact, the hydrated phases are more evident in this case. Note the typical prismatic crystals of Ettringite if compared to the other two. So it has a more porous structure. Instead, mixed seawater in particular, and also mixed SEACON, has a more dense structure, and so the hydrated phases are not recognizable in these two cases. So we decided also to perform MIP to understand the pore distribution, and in fact in the graph you can see that mixed seawater has a lower total porosity compared to the other two mixes, and this is in accordance with what we saw in the SEM images. Then we produced the same mortars and we stored them in dry conditions at 50% of relative humidity to see what happened. And from the pictures you can see that the mixed reference has also in this case a best structure. So the hydrated phases are recognizable also in these cases, but the structures are different from the other one. So we perform MIP also in this case, and we can show that mixed reference and mixed SEACON have a bimodal distribution. They have two different families of pores in this case. The first one is around 0.1 micron and is typical for this type of materials. Instead, the other one is around 1 micron, so bigger pores, and this is completely different from the other case, so water curing, because in this case the development of the hydrated phases is not complete. So the bigger pores are in this case empty, except for mixed seawater. In this case it doesn't have the bigger pores due to the salts that precipitate in them, closing them. So a brief overview of the ongoing durability studies. We are performing tests on the resistance to sulfate attack, because as it's very important to understand if an ionic exchange between chloride and sulfate can happen, and so we are performing this test. Then we are checking if an alkali-silica reaction can occur, because alkali are present in both seawater and in kiln dust, so we would like to check if it can occur. And then an evaluate analysis. This is important to understand if a concrete contaminated by chloride can contaminate also with a release the surrounding soils, and so the surrounding structures, probably with corrodible steel as reinforcement. So we performed this test producing the 3 concretes that I told you before. We produced cubic samples. We stored them for 28 days in a wet room, and then we submerged them in a fixed amount of deionized water. And in different times, we extract the water, so the contact solution, and analyze through ionic chromatography the release of chloride and sulfate in water. So from the graph, it's easy to understand that a higher chloride amount inside the concrete results in a higher release of them. In fact, the mixed seawater presents a higher release of chloride, and instead mixed reference presents a negligible release of chloride due to the negligible content of chloride. Instead, for sulfate, this thing is different because we have to consider the possible ionic exchange between chloride and sulfate. So when chloride are released, sulfate aren't, and so the opposite, when chloride are not released, sulfate are. In fact, mixed reference results in a higher release of sulfate because probably they are not bind as in the other 2 cases. So, in conclusion, we can say that the chloride effect is very important in the hydration process of the cement, and we investigated it through XRD analysis. So we proved the formation of friedel salt. Then a densification of the microstructure was proved through SEM and MIP investigation. And then the contamination of chloride does not significantly affect the compressive strength in both mortar and concrete, but it produces an acceleration of the setting times. And finally, a very strong effect of chloride was observed concerning shrinkage behavior, and it was demonstrated. We have to completely clarify this phenomena and then to find a mechanism to counteract it, maybe using some admixtures or adding some CSA. We wrote 2 different papers. The first one was published in the International Cement Research last June, and the other one will be presented in the 14th International Conference of Durability of Building Material and Components at the end of this month in Ghent. Thanks for your attention.
The producer told me that I have to be on this side, otherwise I cannot work. So that's the only reason I'm coming. Any questions for the excellent presentation by Federica? There will be a quiz on the chemistry of cement after. All right.
Now, the chloride, I know in this project that we're working on, the whole river bridge, we use a fiber rebar, which the chloride should not be really affecting the performance of this material. But let's say we use it with conventional rebar, steel rebar. Would that work in this case with the chloride content?
I don't think so. We need to use a different kind of rebars to permit the higher chloride content. And this is the objective of this work, this project. Because
So it will not work with the
conventional steel, yeah. Because it can create corrosion, yeah. So.
Actually, the next, not the next presentation, the one coming from Polyamine will address this issue of corrosion of black steel or carbon steel in a very high chloride content.
Slide 7, you had showed the friedel salt formation for each of the mixes except for the reference.
Yeah.
And then you have different plus marks there.
Okay.
I assume is indicating different formations. Are you saying that those are different type of formations of friedel salt? What is the significance of the difference?
The plus means a higher or lower amount, and it depends on the chloride content in the materials.
One
waste materials such as kiln dust, the price is lower. So I think that SEACON cement will cost less compared to the reference one, so a normal cement, because we can reuse materials that instead have to go disposal. No. I think 10% less, but I'm not sure about it.
Maybe a question for the producers. Can you hear the questions, or should the speaker read? Okay, you can hear in the back. Okay,
Okay.
perfect. Just any other questions for Federica? Hearing none, thank you very much. Okay, the next presentation is Morteza Katib on behalf of the team at the University of Miami. Let me mention, since we are on time, a couple of items, and as you get ready. There is not much that you can do in the university environment without the contribution of the students, and they are really the brain of the entire operation, so we need to recognize it. There is a bunch of them in the room, not only from UN, but I also want to recognize a colleague, Professor Rodeberry. In addition to this project, there is another project funded by the Florida DOT called the monitoring of the Halls River Bridge, and my colleague from FSU is the PI of that project. She's here with one of her students. So I think also there is a dramatic opportunity for all of us, not just in the state of Florida, but around the country, to collaborate on these topics of research and education. So we're trying to, I guess, instill in the next generation of engineers the importance of the deployment of innovations. Again, for some of you are in industry, if you're looking for great people, maybe you can interview them on the side during the breaks. And with this, I hope that Morteza is ready. But he cannot be hired yet. He has not graduated. He still has 1 year to go.
1 year to go.
Okay, he's not going anywhere.
It's 1 year, sure?
Yeah.
1 year?
Problem.
Okay. So good morning, everyone. Thank you so much for coming. Really appreciate it. And you gave us this great opportunity to present our research. So today I'm going to talk about the WP2. So just to give you an idea, you know that we have different work packages. The first one that Federica was talking about is going to be mainly focused on the properties of the concrete and using recycled material and also high chloride content cement and seawater, and make sure that it's not going to affect the properties of the concrete. So our focus on WP2 going to be on the reinforcement. So for sure, we all know if you use those kind of material, for example, seawater or any kind of raw material that has a high chloride content, you cannot use a sea reinforcement. I mean, it doesn't make sense, right? So you have to find a replacement for it. And there are replacements out there. So these projects going to actually work on cover two of them. And WP2 going to be about the GFRP reinforcement, so glass fiber reinforced polymers that we all know that it's not going to corrode. So it's going to be the best replacement for steel in our project, right? Okay, so the outline, first I'm going to talk about what is WP2 and what are our tasks, and also I'm going to talk about the durability of the SEACON concrete. We didn't spend that much time on that, but because WP1 already covered most of the parts about the concrete properties, but we actually going to focus more on the durability of the embedded GFRP bars. So to make sure that this kind of concrete not going to affect your GFRP bars. And then I'm going to go to what we have done till now, what we're going to do in the future, and the last part going to be the support work that we collaborated with our colleagues about the Halls River Bridge. Okay, so what is WP2? WP2 is we want to make sure that the concrete that our colleagues in WP1 they casted is going to be okay for our GFRP bars. It's going to be good, so it's not going to affect our GFRP bar durabilities. And the output, there's going to be evaluation of the expected life. So we want to make sure that the lifespan of our structure, you're using SEACON plus GFRP bars. going to be guaranteed over at least 100 years. And then the tasks, the properties of the GFRP bars, for sure the pristine bars to test it and then use it as a benchmark. And then we actually use reinforced samples using the new type of concrete, which is SEACON, and we're going to see how it's going to perform. And then also for sure we're going to have some recommendations for the demo project, which is going to be the Hudson Bridge. Okay, so over here, first I want to talk about the mixes that we have used. So in WP1, they use lots of different mixes, but we decided to just focus on two main concrete mixtures, which is mix A, as you can see here. So that is conventional concrete. That's what we use every day. This is type 4 FTOT concrete mixtures that they use for pavements. And that's basically what they use every day. And then what we did for mix B, which is our seawater concrete, we just replaced our fresh water in the conventional concrete with seawater. That's the only difference that happened in that mix B. But for sure, because of the chloride content of your seawater, it's going to affect your setting time. So you have to use different kind of admixtures, for example, retarders, to control that. And you can easily do it by using different kind of admixtures, mainly retarders. So over here, so we actually casted some samples 2 years ago. Before actually the official start of our project, we casted samples from the mix A, which is a conventional concrete, and then mix B. So we casted them, and then we exposed them to different environment to make sure that they are durable in both environments. So the first environment is going to be just outside our lab in Miami, Florida, so basically tropical environment, and the good weather in Miami, right? And then we go to the second environment, which is the tidal zone. So again, we had opportunity to expose our samples in actually in Key Biscayne, Florida. So we just put those cylinders in those kind of boxes, and then we expose it to the tidal zone. And they have been there for 2 years. So we actually went there and we take out our samples after a year, and then after 2 years. So you can see on the graph, so that's the age days. So we tested our samples for the 28 days moisture curing, and then after that, we moved the samples to those two environments. After a year, you can see that they perform, it's really comparable. I mean, you don't see that much effect of the environment, nor the seawater concrete. So you can see mix B, which is the yellow one, actually had a higher compressive strength over 1 year. And then you can go to 2 years, still your seawater concrete, which is mix B, is still higher after 2 years. And then the other, so the solid line gonna be the tropical environment, and then the dashed line gonna be the tropical zone. So the tidal zone. So still, even for the tidal zone, which the samples were exposed there, the compressive strength after 2 years and also 1 year was higher for mix B. So these are the results after. So we just actually did the compressive strength test to see how it's going to perform, because we wanted to make sure that the concrete which is around our GFRP bars going to be good, and we can easily compare it to. So we actually get rid of that variable, because when you gonna study the durability of the GFRP, one of the main parameter going to be the property of your concrete. So you have to make sure that the concrete is good. So the concrete, you can actually eliminate concrete as one of your variable in your durability study. So the concrete good, the concrete looks good after 2 years, and then we go to our embedded GFRP bars. So what we did, we have the concrete, then we want to make sure that the GFRP bar going to perform good when you embed it in concrete actually. So what we have done, we casted samples. This is actually phase 1 of our project. As I mentioned, we casted samples 2 years ago, which is actually 1 year before the official start of SEACON project. So these are the samples that we casted that time. And as you see, it's like a GFRP bar, and the middle part, which we are actually going to run tests on them, is going to be embedded in concrete. And then we expose it to the tidal zone. So the same area as I showed it in the last, in the actually previous slide. If we can, okay. There we go. There we go. that tidal zone, we have actually rainfall samples over there as well. And then after a year, we went there and we, yeah, it likes to go to this slide, I don't know why, but yeah, here we go. So we extracted the bar, and then we run one type of test, they call it horizontal shear strength. This is one of the most important, actually, property of the GFRP bar, so we have to make sure that that's a really good test for quality control. So after we extracted our bars, we ran the horizontal shear strength test. You can see the test setup over here. So it's like the three-point bending test. You put your rebar, and then you actually apply your load at the mid-span, and then you got to see this kind of failure. So basically, it's going to be the shear, the horizontal shear between your glass fibers. So that's what we did. And then, as you can see in the graph, these are the results after 1 year. So we went there, and then we extract the bar after a year. And then you can see mix A, which is conventional concrete, mix B, which is your seawater concrete, right? After a year in tropical environment, we actually got higher results for our embedded bars in mix B, which is seawater concrete. And then you go to the tidal zone. So the tidal zone, the results is still comparable. I mean, you can see that it's like both of them are above 5 KSI. So they are still comparable. And after a year embedded in GFRP in seawater concrete, you can see that we don't see any difference between basically still comparable between mix A and mix B. So the seawater concrete not actually has not a significant effect on your GFRP durability after a year. So we just wanted to make sure that everything all right in the microstructure as well. So we did some SEM imaging of our extracted bars. As you can see, mix A, which is the conventional concrete, this is the bar that I extracted from mix A. And this is the pristine bar. This is the bar that you get from the manufacturer right away after they produce it. And this is mix B, which is the bar that I extracted from from seawater concrete. And you can see no degradation, basically. So this one was phase 1. Then we officially started the SEACON project in October 2015. So in that time, we started actually casting more samples. And what we did, we embedded GFRP bars in these type of beams. So these beams are about 6 feet long, and the cross-section going to be 6 to 7.5 inches. So these was supposed to be the same as the test blocks that we are having in Halsey Bridge. So the main idea was to have some samples in the lab and expose it to accelerated conditioning. So we're going to have test results in the lab and also in the field. So it's going to be easy to compare. And as you can see here, we casted those samples. They have 4 number 5 GFRP bars. And then we expose them to a condition called accelerated environment. And what is it? So it's a seawater at high temperature, 60 C or 140 Fahrenheit. So that's actually what it does. If you want to really study the durability of GFRP bars, you have to wait for 20, 50 years, go to the bridge, take your sample, and then test it. For sure, you don't have that much time, right? So the best way is just to accelerate everything. This is like a time machine. So you just put it in that seawater chamber. You just leave it over there for a year, and then you take out your samples, you extract your bar, and you're going to test your bar. So that's actually basically what people do to make sure that, and then so that based on the models that are available, you can predict that 1 year is equal to, for example, 50 years in the real world. So that's really a time machine, right? So that's what we did, and we exposed our samples in the seawater at 60 C, and that's fresh seawater coming out from the ocean, because we have at UM we have a lab next to the ocean. It's actually our marine school. So we are having the fresh seawater coming out of the ocean every day. And then we have heaters, so they heat up the seawater. And we had it over a year over there, and then I'm going to present the results for that. So we extract the bar, and then we are running the tensile property test, horizontal and transverse shear test. These are the mainly most important tests that they use for quality control of the GFRP bars. And also we did some microstructure imaging to make sure that everything is also all right in the microstructure. So these are the results after year. So as you can see, the tensile property. So the most important property that most of the people they care about is the tensile, right? So we extracted bar, and then we pot them at the ends, so we can easily grip them through the tensile machine, and then we test them. So this is a pristine bar. This is a bar that you get brand new from your manufacturer. This is after 6 months. So after 6 months, we went there, we extract the beam, we take out the beam from the chamber, we extract the bar, and then we test it. So as you can see, actually the tensile strength went up after 6 months. So we had a higher tensile strength after 6 months, and also the chord modulus. So basically the tensile properties of our rebar improved over time. So that could be related to the cross linking of your GFRP bar. So the test also continuing. So after a year, we went there again. We extract more bars, and again, as you can see, after a year, still they are the same. So after a year into the accelerated conditioning, you're getting almost the same tensile strength after a year. And also the chord modulus, you can see, is still comparable. So we go to other test, horizontal shear test. So that test, again, I showed it. It's a really good quality control test. And the test setup I showed you before. So that's the type of failure that you can get. So this is pristine bars, and then this is 6 months. So for actually mix B, which is a seawater concrete, we had a higher results after 6 months. And then when you go to 1 year, although the tensile strength, the shear strength go down, but still mix B, which is a seawater concrete, has a higher results for the horizontal shear strength. And then you go to the transfer shear. So transfer shear, you have a bar, and then you apply your load at the midspan. And as you see again, this is a pristine bar. 6 months, it went down, but it's still comparable. After a year, well, you have to know that accelerated conditioning, the property of the bar is supposed to go down, because that is a really, really harsh environment. You have it inside the concrete, and that's actually almost a boiling kind of seawater. So that you have chloride, all kind of chemicals in the seawater, and also the temperature. So those are all affecting. So going down, it's not a bad thing. We are expecting that this goes down, but it's really amazing that for seawater concrete, actually we got higher results in also horizontal shear and in transfer shear after a year. So it seems that seawater concrete actually helps your GFRP bar, the durability of your GFRP bar. So we wanted to make sure that in the microstructure also we are all good. So we took some SEM imaging. This is actually after 6 months. We haven't done it for a year, but this is after 6 months. And you can see again, this is pristine bar. So we take a picture at actually the edge of the bar, which was in contact with the concrete, and that's actually the most the most important area, because it's very prone to all the damages. Whatever going to happen is going to start from the edge. So if you take a picture from the edge, nothing happened in the edge, basically you are pretty sure that nothing going on in the middle of the bar. So that's why we took a picture at the edge, and again, as you see, this is mix A, this is mix B, no degradation, right? So we did all those tests, and that was actually we're going to conclude till now. And as you know, this project going on, and we're going to have results after 2 years, and then based on the results that we're going to have, by using the models available right now in the literature, we can easily say, okay, based on these results, the GFRP is going to be okay for 100 years or 200 years. So the fresh and harder concrete properties, WP1 went into details, but that's based on the compressive strength results that we got. Actually, seawater concrete after 2 years performed better than the conventional concrete. So the mechanical behavior of SEACON, as I mentioned, was actually better compared to the conventional concrete. The mechanical and physical properties of the embedded GFRP bars, again, we were expecting to go down, but we saw better results for seawater concrete. And then microstructure, SEM imaging didn't show anything, so no impact actually on the microstructure of the concrete due to using the seawater concrete. And then for sure, we are using all these as recommendations for our halls, for the demo project, which is Halsey Bridge, and we're going to all see it tomorrow. So what we're going to do in the future, we're going to focus more on seawater concrete, see what it has that's going to improve actually the property of our GFRP bars. So we have to do some tests on the concrete by itself. So kind of get involved more with WP1 and work on the durability of the GFRP and make sure that everything all right in the concrete. And then by you doing that, we're going to understand why the property of our GFRP bar are going to improve by using seawater. And also, we keep going with our other tests on our GFRP bars. And over here, you see our time span. So we keep going. This is for the next 6 months. And we're going to be busy for the next 6 months testing all our samples. And also, the other important property of the GFRP bar is a bond between the GFRP and the concrete. So we also casted some samples to study that. And we're going to actually focus more on that in our next 6 months. So I'm going over quickly over the what we have done as support work to for our colleagues in Astaldi and our colleagues involved in Halsey-Webb Bridge. So we actually designed the mixture, concrete mixture designs that they're going to use in Halsey-Webb Bridge. And so after designing it, we went to Argo's ready mix plant, and they were kind enough to have us over there. And with FTOT representative, we did all the trial batches, and they all got approved. And as you can see, that we have a structural and non-structural. So we have class 5, which is 5,500 psi. That's the normal concrete that they use. Then we have green class 5. That's actually class 4. Sorry. So green class 4. That's class 4. You replace the fresh water with seawater. So that's why we call it green, because it's really green, and the amount of fresh water that you're going to save, it's amazing. So we go to 100% white cement. This is 5,500. Also, these are for the railings that our group did the designing of the railings also. And we have the 60% of the slag. So what we want to do, we want to make sure that that 60% slag, 40% cement is going to have, because the color going to be, we want to have the white railings, right? So we wanted to try both to see how they're going to perform, and also they're all going to be reinforced with GFRP bars. And then non-structural, which is really interesting, we are using recycled concrete aggregate, and we are using recycled asphalt pavement. And these are going to be used in the gravity walls of our Halsey-Webb Bridge. And we added 2 more mixers that we're going to use. We're going to cast samples for our the research purpose. We call it green RCA and green wrap, which is going to be super green because you're going to use seawater and also recycled aggregate in it. Really sustainable concrete. So that's what we have done. And we did all those tests for sure when we got the aggregate, the wrap, and RCA. You have to, when you want to design a mix, you have to do all the aggregate property tests. I mentioned those over there. And also the seawater, you have to make sure what you have in your seawater, because there are lots of chemicals. It's not only salt, it's not only chloride. You have magnesium, you have potassium, all those. You have to make sure that how much you have. So in the future, when you want to go back and see what happened to your concrete, you can easily follow and you can easily track what changes actually has happened because of what chemical element. And then we with the help of the RCA and wrap provider that we have them actually in the room, we delivered the seawater and also RCA wrap to the ready mix plant in Brooksville, the Argos ready mix plant, and hopefully they're going to start pouring the concrete soon, and we're going to see it on the job site. So with that, I'm going to conclude my presentation. This is Sebastian. This is if you ask any question, I'm not going to be angry at that, but feel free to ask any questions. I'll be happy to answer. And thank you so much for listening to me. Appreciate it.
Before we open the floor to questions, I also want to recognize the companies that are participating in the Halsey River Bridge project that are not necessarily the partners and collaborators of the SEACON project itself. So obviously, Astaldi as a general contractor, and we have representation here, and tomorrow we'll hear much more. we have Argos here that obviously is providing the concrete, and Morteza made reference to that. But we also have, for example, the supplier of the recycle aggregate to Mr. Moore somewhere in the audience over there, independent recycling. So I think again, the objective of our work is try to put all these pieces together and create a network with the dialogue among all the various components. So it's not just the ones that you've seen in the SEACON, but there is a host of other groups really very much involved in the work that we're doing. With this said and done, questions for Morteza?
I have a question.
Yes.
About the monitoring of the bridge, the whole river bridge for performance. You mentioned 6 months period that you're going to monitor that. Why not, a year, 2, 10 years?
So actually, we have a project. I guess Dr. Nani going to go over it in detail in a couple of slides coming up. That we're going to monitor actually the bridge over time. We want to make sure that what we casted over there going to work, and that's a great opportunity to compare the results that we get from the real world, from the field, to our results in the lab. Yeah. So we're going to have a project focusing on just the monitoring of the bridge and the samples that we have.
If I could add to that answer, it's the SEACON covers one part, but the project that FSU is leading and Ms. Roddenberry just behind you is the PI, is funded by the Florida DOT for the monitoring of not just the construction, and I would say the initial stage of the life of the Holtz River Bridge. And hopefully there will be a continuation because clearly the Florida DOT will not be satisfied in seeing what's happening after 3 years of time. So I think this will be a legacy for the future, and hopefully there will be more bridges in the inventory. But the plan for continuous monitoring.
You want to start sharing your screen?
I think we are simply now establishing a connection between SEACON and the Florida DOT project. So you will hear more today, and I will say something about the test blocks that we are retrieving from the site to then test it.
Are your two questions? Are your durability studies complete, or are you continuing the durability studies in terms of the duration?
Yes, we actually. So this is 1 year results, and actually we have enough samples for 3 years. So the test going to be continued till 3 years.
And for the GFRP comparison and durability studies, by chance did you measure the moisture absorption and maybe compare it to?
Yes, we did, but I didn't present it here. So we did, but actually they didn't show anything. So you just because when you do the moisture absorption at the beginning, like as a per seam bar, and then you do it after like 6 months. We have the results, but we're gonna go over into details to see actually what's going on. That's gonna give us a really good indication if you want to get any conclusion out of it. Yes, we did actually those tests.
Actually, if I could add to that, you can tell that this is a project very dear to my heart. There is really 2 stages in terms of the R&D that we are conducting. One is a pre-construction, that is the qualification of the material system, and the other one is the performance of that material system over time. So this relationship is very, very important for us, and as you kind of implied, all the tests that are part of the qualification process will be repeated over time to make sure that those fundamental properties, well, they will vary, but they vary within a possibility of us predicting them. So excellent. Any further questions? Yes?
I just want to follow up on input. On slide 9, I think you showed the performance of the bottom 2 mixes.
Let me open that.
But it was only the performance regarding mechanical properties. When you extract the bar or those, and I believe that's what I'm saying, follow up to the when you actually
So the moisture content of the concrete and also the bar?
And or the bar.
No, we just do on the bar, not the moisture content, because your concrete is going to be fully saturated. It's like 1 year in seawater concrete, in seawater.
We have two different mixes. I don't know if the level of saturation is going to be the same. That's what I'm trying to say. What do we usually have?
Okay, so okay. So
But it has affected the bar will be either the concrete itself or the conditions that
yes, so right, we did some tests, and what we did actually, we did to measure the chloride diffusion of the concrete. So the both concretes, right now we have the results for how much chloride get into your concrete and to your bar level. So after 6 months, actually the chloride didn't get to any of it, because we have 2 rows of the bar, one at the top and the one at the bottom. So after 6 months, no chloride to your bar. But after a year, right now, we get some chloride, not in the really high content. But right now we have some chloride that got to our rebar. But the only test that we did on the concrete was the chloride diffusion, and also we did some SEM imaging on the concrete, but not the moisture, the content of the concrete. But that would be a really good idea, I guess.
So if I understand, the suggestion here would be, before we open up the beam, let's call it beam because of the shape, maybe we should core it and really do measurements of level of saturation. Maybe we'll follow up, because I think the trick is, how do we make sure that we do not impact the specimen as we extract it? So we will
follow up for sure.
But we understand the suggestion. Just don't focus on the reinforcement. Tell us more about the concrete itself. Excellent. Any further question? And this is used, and I think Catherine indicated this at the beginning of our presentation. There should be an exchange of not only questions for clarification, but suggestions on how we can improve the work that we have to do, because tons of specimens are still coming. Actually, we have not started collection at Rose River, so we have plenty of time to do the things that you suggest. Yes, sir.
on the specimens that you showed, you do the removal like you just said of the specimen. I was impressed by the results, because now you're removing the specimen from concrete, which might slightly damage the specimen itself. So it's very clear.
Any other questions for Murtaza? Hearing none, thanks. Now,
Thank you.
now we go to a very difficult part, meaning from a, let's say, ability of us to be efficient. So production here is the trick. The colleagues at Polyme are physically in Milan, and they will join us through Skype, and we are trying to also project that. By the way, if you see me playing with my computer, is I'm watching the presentation through YouTube, so I can see the slides there as well. So I leave this to Murtaza to make the connection. Let me introduce Dr. Lolini. Federica Lolini is ready to go, and then after our presentation, we will have a second presentation from Polyme. This is before the break, and Dr. Redaelli will be making that presentation that will be on WP 4.1, which is the demonstration project in Italy. So we're ready to go with WP3, the corrosion tests on concrete specimens reinforced with the stainless steel.
Okay.
Federica, can you hear us?
Hold on. No, I mute her.
Oh, mute her, okay. We're getting there.
Okay.
Yes, beautiful, thank you. Try to speak as loud as you can, and if we cannot hear, I'm sure that we can figure this out.
Yep,
Maybe you want to close the other window.
Yeah, you can start, but hold on.
Okay, that's fine. Do you see my presentation?
Yes, we do.
the activity carried out at Politecnico di Milan on the WP3, and in particular the corrosion test on concrete specimens reinforced with the stainless steel and carbon steel bar. The outline of this presentation is a brief introduction, followed by a brief characterization of concrete for durability related properties, and then the core of this presentation is about the corrosion behavior of carbon steel bars in chloride contaminated concrete, and the corrosion behavior of the stainless steel bars embedded in chloride contaminated concrete, and then some final remarks. In conventional concrete, that is a concrete made with virgin constituents, the chloride content is negligible and then below the standard limits. So, thanks to the microstructure and the poor solution composition, carbon steel bar can be passivated. Then, in time, due to the aggressive agents can penetrate into the concrete, leading to the breakdown of the passive layer, and so initiation of corrosion occurred, followed by the propagation time, which depends on environmental actions. What happens if virgin constituents are replaced with material contaminated by chloride? So it means if one of the constituents has a higher amount of chloride above the standard limits. The chlorides inside the concrete may affect the microstructure as well as the pore solution composition, and so the passivation of the carbon steel bar may be affected. And the presence of chloride inside the concrete may lead to early corrosion initiation and may affect the resistance to penetration of aggressive agents. The durability of sea concrete can be improved by the use of stainless steel bar reinforced. It's well known that the passivation of this type of bar is improved, as well as the resistance to the passivation. So, in Politecnico di Milano, we carried out several tests in order to study both to characterize the concrete, so to study how chlorides affect the resistance to penetration of aggressive agents, as well as the microstructure and so on, and corrosion tests to investigate on the corrosion behavior both of carbon steel and stainless steel bars. Several mixes were made, reference mix with the virgin ingredients, SEM and SEM-FA mixes where the cement were replaced with the SEACON cement that Federica Bertola talked about in her presentation. The C mix where the fresh water was replaced by seawater, and the RCA mix in which part of the coarse aggregates were replaced with recycled aggregate, which were obtained by crushing all the contaminated concretes. Beside these mixes with mixed in chlorides were also cast, in which the chloride content ranged from 1 to 5% versus mass of cement. These are the mixes, this table reports the mixes and the properties of fresh and hardened concrete. The 8 mixes were cast with a water cement ratio of 0.52 and of a workability of S4. Compressive strength was tested after several days of moist curing, and an effect of chlorides in the mixes were observed in the early days of in the compressive strength measured after early curing, and some specimens were also immersed in seawater after 20 days of moist curing. Curing in seawater may affect the compressive strength when the exposure time increase. Other tests were performed in order to investigate on the durability related properties. This slide just summarizes some of the tests which were performed. In the figure above, it's reported the chloride content measured on the different type of mixes. In the figure on the left at the bottom, there is the water is reported, the water absorption coefficient as a function of the different types of mix. These parameters give an indication of the porosity of the concrete. We can observe that mixes SEM, SEMFA, and C has a lower water absorption coefficient than the REF mix. Instead, the RCA mix showed a higher coefficient, and this may be due not to the chloride content in the mix, but to the presence of recycled aggregates, and so to a higher amount of cement paste present in this type of concrete due to the presence of aggregate. On the right, we can observe the result of another test, which is the carbonation test. This is the accelerated carbonation coefficient, which gives an idea of the resistance to the penetration of the carbonation. We can observe that the presence of chloride in the mix didn't affect significantly the resistance to carbonation, since comparable results were obtained on all the different mixes. In order to study the corrosion behavior of carbon steel in sea concrete, reinforced slabs were cast. These slabs were exposed to different environmental conditions. Before they were exposed to an unsheltered outside exposure in Milan, and then some exposure cycles were done varying the temperature and the relative humidity. These tests were carried out in order to simulate a structure where no further chloride penetration is expected. This figure shows, as an example, the corrosion potential, which is presented by the circle symbol, and the corrosion rate, the triangular symbol, measured on the carbon steel bar embedded in the reference concrete, so in the concrete without chloride. Both the corrosion potential and the corrosion rate give an indication of the corrosion behavior of the steel. So when the corrosion potential is low and the corrosion rate is high, it means that the bar is active, so is corroding. We can observe that during the first period of exposure in the unsheltered outside exposure, we had an increase of the corrosion potential and a decrease of corrosion rate, indicating the formation of the passive film. Then we have a further increase in the corrosion potential due to the drying of concrete, and then we had some fluctuation due to the change in the environmental exposure. We do not have significantly variation both of corrosion potential and corrosion rate, indicating that in all of these exposure conditions, passive conditions were maintained on the carbon steel bar, which was expected since no chloride were present. The blue symbols represent the behavior of a carbon steel bar embedded in sea concrete, so concrete made with seawater. We can observe that both the corrosion potential and the corrosion rate were a little bit different from those measured in the carbon steel bar embedded in the reference, indicating that the behavior was slightly different. But what we can observe is that in some condition, in particular when the temperature was high and even the relative humidity, there were a drop of the corrosion potential and an increase of the corrosion rate, which indicate the occurrence of corrosion during this exposure condition. This figure summarizes the results obtained on the carbon steel bar embedded in the different mixes that are represented by the different symbols exposed to the different environmental conditions, which are represented by the different colors. In particular, it shows the relationship between the corrosion potential and the corrosion rate. The gray area in the above part of the figure represents the condition where carbon steel is passive. We can observe in this figure that in the most aggressive conditions, that are those of with the high temperature, so around 40-50 degrees, and the high relative humidity around 100%, the value were below the threshold, indicating that in this condition the carbon steel bar were corroding, and so was active. Carbon steel bar was also active in less aggressive condition, but when it was embedded in the concrete with the highest chloride content, so in the concrete with the 3 and 5% of chloride. So this test showed that, as expected, carbon steel bar was unsuitable when embedded in some concrete with the high chloride content and in the harsher environment. These considerations were also confirmed when the specimens were exposed to the further chloride penetration. As a matter of fact, other slabs were exposed to a ponding with a chloride solution. This figure shows, as an example, the corrosion behavior of carbon steel bar embedded in the ref concrete, and we can observe that the corrosion potential decrease, the circle symbols decrease in time, and the corrosion rate increase in time. This was due to the initiation of corrosion. It means that the further chloride penetration induced the corrosion. So at the level, at the depth of the bar, the critical chloride threshold was reached, promoting the initiation of corrosion. In the carbon steel bar embedded in the sea concrete, we had from the beginning a quite low corrosion potential and a quite high corrosion rate, indicating that it was enough just a few amount of chloride to promote the initiation of corrosion, indicating that the initial chloride content was just slightly lower to the critical chloride threshold. So in 1 year, corrosion occurred on all the carbon steel bar embedded in all the type of concrete, indicating again that the carbon steel bar was unsuitable to be used in combination with sea concrete. So an option is the use of stainless steel. In the work, 4 different types of stainless steel were considered. This steel differs from the microstructure, the chemical composition, and the chemical composition. So we consider 2 austenitic stainless steel, the XM28 and the 304, and 2 stainless steel with a duplex structure, 2304 and 2205. The mechanical strength of the stainless steel is equal to that of carbon steel, but they have a higher corrosion resistance. They are passive in carbonated concrete, and the amount of chloride which promotes the initiation of corrosion is much higher than that of carbon steel bar. The carbonation of concrete may affect the critical chloride threshold, which is still high, however. This figure shows as an example the corrosion behavior of the 4 types of stainless steel embedded in the sea concrete and exposed outside unsheltered and then to the different exposure cycles. We can observe that the corrosion potential of the stainless steel was quite high even in the most aggressive exposure condition, and the corrosion rate was low, indicating that all the stainless steel maintained the passive condition even in the harshest environment. This figure summarizes the results obtained on the different type of stainless steel and show the relationship between the corrosion rate, the corrosion potential and the corrosion rate. The gray symbols represent the results obtained on the carbon steel. These are the results obtained on the stainless steel 304, and we can observe that for the different type of concrete represented by the different symbols in the different exposure condition, high corrosion potential and low corrosion rate were always measured, indicating that corrosion did not occur even when the bar were embedded in the concrete with the highest chloride content, so 5% of concrete, and when exposed to the harshest environment, so the highest temperature and the highest relative humidity. Comparable results were obtained on the duplex of stainless steel 2205 and 2304, indicating that even on this stainless steel bar, no corrosion occurred when they were embedded in the concrete with the highest chloride content and in the most aggressive and exposed to the harshest environment. On the XM28, which is the less alloyed stainless steel, corrosion did not occur in any of the exposure conditions. So these results show that the stainless steel employed in this study are suitable to be used in concrete contaminated by chloride when no further penetration of chloride is expected. In order to study their behavior when the further chloride penetration is expected, the specimens were exposed to the ponding test. These are the results obtained during 1 year of exposure on the different type of stainless steel embedded in the sea concrete. So, besides the initial chloride content, we have to take into account the further penetration of chloride. We can observe that both corrosion potential, the gray symbol, and the corrosion rate, the black symbols, were stable during the exposure period, indicating that corrosion did not occur during this year of exposure. So next steps will be to evaluate the chloride content at the depth of the bar reached after 1 year of exposure, in order to compare the chloride content that we have now at the depth of the bar to the chloride content which is expected in a real structure after maybe 50 of 100 years of exposure, in order to investigate even if under the further chloride penetration stainless steel bar can be used in combination with sea concrete. So, to conclude, the test aimed at studying the role of chloride-contaminated raw materials on the concrete transport properties showed that in the case of the mixes studied in this work, chloride contamination does not significantly affect the concrete properties. However, based on preliminary results, curing in seawater might affect the strength of concrete with the increase of exposure time. Corrosion tests on reinforced concrete slabs showed that in absence of any further penetration of chlorides, and it can occur for structures far from the sea, No corrosion was induced on any of the stainless steel bar employed in this study, even when 5% of chlorides were mixed in and when the slabs were exposed to the harshest environmental conditions. Conversely, carbon steel bars showed to be unsuitable in the harshest environmental condition when embedded in the thick concrete. The further penetration of chloride ions led to the initiation of corrosion on the carbon steel bar embedded in the different mixes, suggesting that the initial chloride content, due to the use of chloride-contaminated raw materials, was only slightly lower to the chloride content, which promotes the initiation of corrosion, that is the threshold, critical chloride threshold, in the studied exposure conditions. The further penetration of chloride did not lead to the occurrence of corrosion on any of the stainless steel bars embedded in concrete made with chloride-contaminated material. Thank you for your attention.
I think we could move directly to Dr. Reda's presentation. I think it's going to be difficult for us to ask questions and expect them to reply. I think just yeah, probably the best is. Okay.
Good.
Yeah, I think the best is to ask them to continue.
Okay.
Okay.
So I guess you heard us, right? Did you hear us?
Yeah?
Okay, so we can just keep going with the WP board. Elena can take over.
Yeah.
Thank you so much.
Okay.
You can stay where you are. We will team up.
Okay. Can you hear me?
Yes, we can.
Okay. Okay, good morning, everyone, and thank you very much for the support for this connection. I will present the preliminary results of on-site monitoring of the field demonstration project in Italy. This is an outline of my presentation. After a short introduction on the WP4 in Italy, I will present the construction of the culvert of the structure, and then I will describe the methodology that we have used for the monitoring of corrosion. And I will present some of the preliminary results that we have obtained so far. And then I will go to the conclusions and to some possible future activities. The main objectives of this work package are to design, construct, and monitor a demo project in Italy using seawater concrete together with both stainless steel reinforcement and also GFRP reinforcement. Specifically for our group, the aim is to monitor the long-term durability behavior of this structure beyond the end of the SEACON project and also beyond the duration of the experimental activities. Several other partners were involved in this WP, and in particular there was Buzzi. They designed the concrete mixes and they characterized also the concrete and they supplied the concrete on site. Then there was Pavimental, who made the site available, and also they were in charge of the design and execution of the project, and they also made available the workmanship for the construction itself. And finally, Acciaierie Valbruna and ATP, who supplied the stainless steel reinforcement and the GFRP reinforcement. And I would like to acknowledge the contribution of all these participants because they were all essential to the achievement and to the success of this project. The site that was chosen is an asphalt production unit of Pavimental that is located in Pontenure, close to Piacenza. This site is close to A1 motorway, to the exit of Piacenza Sud, and it is in the northern part of Italy, about 80 kilometers south from Milan, so not too far away from Milan. The structure that was built is a reinforced concrete culvert that runs parallel to the roadway. Actually, is only a few meters away from the road, and that collects the wastewater that are contaminated by chlorides, at least during the winter season when the de-icing salts are used on the road. Overall, the culvert is 30-meter long, and it is divided into 6 individual and independent segments that are 5 meters long each. And each segment is representative of a different combination of type of concrete and type of reinforcement, and so we will see in a moment. This is the section of the culvert. The culvert is made of a slab that lays on the soil that is about 80 centimeters wide and 15 centimeters thick, and it is reinforced, and it is surrounded by 2 inclined side walls that are non-reinforced, and they are made with ordinary concrete. The reinforcement is in the form of a mesh with spacing of 20 centimeters, and the cover, the thickness of the concrete cover of all the reinforcement is 30 millimeters. As I said, each segment is representative of a different scenario, so a combination of type of concrete and type of reinforcement, as it is summarized in this table. So segment A is a reference, so carbon steel reinforcement in chloride-free concrete. Then there are segments B, C, D, and E that are all made with seawater concrete that contains seawater, and contain respectively carbon steel reinforcement, stainless steel 304 that is an austenitic grade of stainless steel 2304 that is duplex stainless steel, and finally GFRP reinforcement. And finally, the segment F is made again with carbon steel and RAP concrete. That is a concrete that is obtained by a partial replacement of coarse aggregate with recycled asphalt pavement. The concrete contributions that were designed in agreement with Buzzi are reported in this table. So basically there are 3 different concretes: the reference concrete, the SEACON concrete that is the same as reference but contains seawater instead of fresh water, and finally the RAP concrete that contains, as I say, the partial replacement of recycled asphalt pavement that comes from the same plant of Pontenure where the demo project was located. The aim of our activity is to monitor the corrosion conditions of the reinforcement in order to detect the possible initiation of corrosion in time. And to do this, we used different types of probes. First of all, we used a reference electrode of the type silver-silver chloride that is used for potential monitoring. Then we also designed some multiple reinforcement probe. Each one contains all the 3 different types of reinforcement, carbon steel, stainless steel of the 2 different types, and also an additional reference electrode made with titanium. And the aim of this multiple probe is to allow to simulate all the possible combination of concrete and reinforcement, even the one that could not be achieved for practical reasons. And finally, we used also a resistivity probe that allows to measure the resistivity of the concrete, the electrical resistivity of the concrete. All these probes were embedded inside concrete next to the reinforcement, so at the same depth of the reinforcement, at the same depth of the concrete cover. This is a summary of the electrical connection. Obviously, every probe was connected with a conductive cable, and all the connections were taken outside in order to make the monitoring easier. As you can see, apart from the probes that I mentioned before, segment B also contains an activated titanium mesh that was placed at the bottom of the slab And this is intended to be used in the future for possible electrochemical tests or even for the application of cathodic protection. While in segment E, that contains GFRP reinforcement for which electrochemical test cannot be used, basically we used only the resistivity probe. These are some of the stages of the construction of the slab. The rebars were assembled in the form of a mesh on site, and they were placed at the bottom of the slab. The side walls had been cast a day in advance compared to the slab. Then we installed the probes that, as you can see from these photographs, they were fixed at the reinforcement so that they were exactly at the same depth. All the connections were taken outside and connected inside this electrical box. And of course, before casting, we checked that all the connections were working properly, and they were, at least in the beginning. Then the concrete was cast in 3 different batches, and it was compacted through vibration and cured by covering the surface with a waterproof foil. It was a very rainy period, the time when this demo project was built. And this is the appearance of the culvert at the end of the construction that was completed by the end of November last year. As you can see, inside the culvert, we also exposed some sacrificial cubes of the same concrete that were cast on site in order to be used for possible future analysis and to reduce the invasiveness to the culvert itself. Now I will describe the methodology that we have used so far, both on site and in the lab, in order to monitor the corrosion conditions of the reinforcement. Well, first of all, we measured regularly the potential of the reinforcement and the electrical resistivity of the concrete. So far, these measurements were done manually because the data acquisition system that we had planned to use is not ready yet. So we performed this measurement manually more or less once a month in the last 5 months of service. Then after 5 months, which is basically last week, we also made a potential mapping. So we measured the potential of all the grid in each segment with respect to an external reference electrode. And finally, we also performed some analysis on the concrete cubes, on some of the concrete cubes that were taken during casting. In particular, chloride content. However, I will not discuss this today because we had some strange results that we are still going to clarify. And also we measured the electrical resistivity during the first 28 days of wet curing of the cubes. These are the results of potential monitoring, and in particular, these are the potential that were measured with respect to the embedded silver chloride reference electrode. On the left, the potential of carbon steel in reference seawater and RAP concrete, and on the right, the potential of the 2 types of stainless steel in seawater concrete. We can see that in all cases, the potential was rather low in the beginning, and then it showed an increasing trend. After about 5 months, we can see that all the potential are quite high, and in particular, all the potential of carbon steel in reference and RAP concrete and also stainless steel is higher compared to minus 100 millivolts. Only the potential of seawater concrete is about, of carbon steel in seawater concrete is about minus 200, which is quite lower compared to the others, but still is a relatively high value of potential. What we did so far was to compare these results with the one that we obtained from the laboratory specimen in similar exposure condition, and we can see that there was a good agreement between the two. Of course, it is quite difficult to interpret these results. They need to be monitored for longer periods of time. But because of the relatively high values of potential, we can assume that both carbon steel in reference concrete and also the two types of stainless steel in seawater concrete are not actively corroding. At least they are not yet actively corroding. We perform also potential mapping. These are the maps that we obtained. The colors are not really meaningful, but the aim of this mapping was to check the corrosion condition over all the segment that is 5 meters long. We should remember that when we use an embedded reference electrode or any other probe, we obtain information on the potential or any other parameter in the vicinity of the probe itself. So with the potential mapping, we can see whether the condition is the same also in the areas that are farther from the probe. Actually, we can see that the variation in the potential gradient inside each segment were only of few tens of millivolts. So the potential was quite uniform in all the segments. And so we can consider that the results that we obtain from the probes, at least so far, can be considered representative of the conditions in all the segments. These are the results of the resistivity, the electrical resistivity of concrete, on the left on-site, and on the right on the concrete cubes in the laboratory. On-site, we can see that there are some variations in the resistivity, and in particular, we can see that the resistivity of the reference concrete and the RAP concrete were more or less always lower compared to the resistivity of seawater concrete. And this is quite strange because the contamination with chloride is expected to decrease the resistivity. However, we should consider that on-site, of course, there may be the penetration of chloride, although it is unlikely that chlorides have penetrated the concrete up to the depth of the reinforcement, that is 30 millimeters. There may be also other factors that can affect the resistivity, like, for instance, the local conditions of humidity, the temperature, and so on. And in fact, when we measure the resistivity in the laboratory on the cubes, we obtained that the resistivity of seawater concrete was always lower compared to the resistivity of reference concrete. Of course, also these parameters need to be monitored for longer periods of time in order to be better interpreted. So the conclusions of my presentation are that the results of monitoring of the corrosion conditions during the first 5 months of exposure indicate that the rebar potentials are in agreement with the one that we obtained on reinforced specimen in the lab in similar conditions of exposure. Stainless steel rebars in seawater concrete show a very similar behavior as carbon steel in reference concrete, and we can assume that they are both not corroding yet. Further analysis for sure are needed, specifically the measurement of the depth of carbonation and the chloride profiles in order to better understand the corrosion behavior. For the future activities, of course, we plan to go on with monitoring the potential and the resistivity, hopefully with the data acquisition system, and to analyze the chloride profiles and the advancement of the carbonation also in the sacrificial cubes. And finally, we also need to define suitable tests in order to investigate the behavior of GFRP rebars. And this is all. Thank you very much for your attention.
I think we are just a couple of minutes over time, so you deserve a break. So we'll skip the questions, and if you email them to me or Morteza or the speakers, and we will take care of that. But before we break, I would like to remind that